Phenomenon-based teaching. Why does this teaching methodology make sense? It encourages students to ask questions. It facilitates their ability to discover connections, and it encourages them to design models so as to make sense of their scientific observations. In this video, I'm going to take you through this following phenomenon involving the decomposition of copper-2 carbonate, and I'm going to focus on 6 different questions relating to 6 different concepts that can literally be extracted, so to speak, from this particular phenomenon. Let's get started. First, I encourage my students to ask, what again are the physical states of matter? Second, does the phenomenon involve a chemical or a physical reaction? Third, is the reaction endothermic or exothermic? Fourth, is a gas produced, and if so, is it an acid or a base? 5, how can we best model this reaction? And 6, since we're modeling anyways, can we actually draw electron dot diagrams of the chemical species involved in this reaction? Let's go. This GIF animation shows you the actual decomposition of copper-2 carbonate, starting with a green powder turning into a black powder. This is actually the 3rd chemical reaction that I'm sharing in the video linked above. The 3rd out of a total of 7 key chemical reactions that I've done with my students in my classroom. Check out the video if you want to see the remaining 6 chemical reactions. So in order to encourage student participation, I use PearDeck in my classroom. All my students have a Chromebook, and the PearDeck app enables them to write their answers either by typing or by drawing at their own pace. This particular image is actually hyperlinked to the PearDeck site, and this particular interactive slide bar is key, what you need to have on a given slide for students to be able to draw anywhere on the slide. You can then show as a teacher the answers that students have given in the classroom. If you get the paid version, you have your school pay for it, please, then you can pre-screen the answers that students have given, and these answers that you can display for everyone to see are anonymous. It really encourages student participation. All right, so physical states of matter. What are we dealing with right here? Clearly, we're starting off with a solid reactant. I don't see much of a liquid happening, and I know that there is a gas formed, but can we see that gas right now? Second question that I encourage my students to answer: is this reaction, this phenomenon, chemical or physical in nature? The fact that we're using this butane burner to keep this reaction going suggests that there is clearly an energy change happening. Obviously, there's a change in color. We're going from a slightly greenish color to a more blackish color. But is there a gas released? I don't know. You can't really smell anything. You don't see any fizzing. So how can you find out? Different setup here, same reaction. We're siphoning off the gas. It's released in this flask. Clearly there's bubbling. Based on these 3 observations combined, we can confirm that this is a chemical reaction. We are not seeing a frequently observed 4th type of evidence, namely the formation of a precipitate, but since this is not a double replacement reaction, there is no liquid in sight at this moment. 3rd question that I encourage my students to answer is whether this reaction is endo or exothermic. And if they can figure it out based on the continuous supply of the butane flame, they should actually be able to draw the energy diagram, the potential energy diagram. So they can come up with something fancy like this, where we start low, we end up high, but what does that mean in terms of bond strength? And I encourage my students to use the bicep image to emphasize the strength of the bond. So strong bonds are broken and weaker bonds are formed, hence this reaction again is endothermic. The video linked above concerns endothermic reactions and goes into more detail how best to model these. 4th question: What about that gas product? Is it an acid? Is it a base? Let's check it out. So you're seeing my student here adding some universal indicator that clearly must have some bromothymol blue in it. After adding the copper 2 carbonate to the test tube, we're going to heat it up again with the butane burner. The gas is going to be released in the flask, and over time, watch how that greenish color slowly turns into a more yellow color, suggesting that the gas must be acidic in nature. This is a writable slide, as you can see with that little PearDeck link below. This gives students the opportunity to really take a look at these colors, what might be the associated pH, and what may give rise to the change in color. The indicator solution looked more greenish to begin with a roughly neutral pH, and as more and more carbonic acid was entering in this flask, the indicator's color changed to a more yellow form, showing you that the solution has become more acidic. If you'd like more help how to teach your students about acid and bases through student inquiry-based learning, check the link above for more details. So we've watched that decomposition of copper 2 carbonate. How can we now best model this reaction? Well, we're starting with that beautiful bluish copper 2 carbonate. Clearly, we need a lot of heat, a lot of energy to get that compound to decompose. Strong bonds are broken, hence the bicep image. There clearly was a gas release. We saw that bubbling. And because the reaction is endothermic, that means weaker bonds are formed. We're ending higher on the potential energy curve. But besides the carbon dioxide, we also formed the black copper 2 oxide. This particular slide shows you a model that's more at the atomic level. Copper 2 carbonate again, with a lot of energy input, will decompose into carbon dioxide and copper 2 oxide. Many videos on my channel are focusing around the storyline, why do some things get colder or hotter when they react? The link above is the featured video that highlights the storyline, and it culminates into the students creating a model surrounding the bonding phenomenon. And if you wish to review or delve deeper into the modeling, you can go next into electron dot diagrams. I really enjoy the PhET interactive simulations. They have one particular simulation titled Molecule Shapes, and you can either model mock molecules or actual real molecules. And you're seeing here on the screen a 3D model of water versus carbon dioxide, and then you connect this so-called VSEPR three-dimensional structure with the two-dimensional electron dot diagrams. This particular phenomenon-based lesson centers around the following next-gen science standards and New York State Science Learning Standards, HSPS1, Matter and its Interactions. If you wish to get access to all these beautiful slides and use them with your students, simply go to the description below, and there's a link ready for you to click on, and these slides can be yours to use in your classroom. Dutch lesson for the day. In this decomposition reaction, the gas that was released is carbon dioxide, CO2. What do we call that gas in Dutch? Kooldioxide. Kooldioxide is really short for koolstof, stof material, dioxide, dioxide. Not too different from the American word. But when you mix carbon dioxide with water, they combine to form carbonic acid. And that we call koolzuurgas. Repeat after me. Koolzuurgas. Kool, carbon. Zuur, that's the acid. And gas is, of course, gas. Thank you very much for watching this video. Bedankt voor het kijken. Tot ziens and see you in the next video.